Chemistry. Today we're going to study a process of determining the energy in a chemical reaction by measuring its heat. It's called calorimetry, and this is a process that you're going to actually carry out in a couple of experiments in the lab. So calorimetry is a process where the heat of a chemical reaction is released into a container of water. The temperature change in the water can be used to calculate the amount of heat using the equation Q equals mc delta T. This is the amount of energy released or absorbed by the chemical reaction in the form of heat. Constant pressure calorimetry, also called coffee cup calorimetry, is carried out in a container open to the atmosphere. So if it's open to the atmosphere, it's not pushing against anything. It's just at normal atmospheric pressure. The pressure remains the same. Therefore, it's not doing any work. And therefore, all of the energy from the chemical bonds, none of it is going into pushing or moving anything. It's all simply going into heat. So if we can measure the amount of heat or figure out the amount of heat, then we'll know how much energy came out of the chemical bonds. So this means that the process always maintains the pressure of the atmosphere of the room. That's constant pressure. Constant pressure calorimetry consists of these steps. We will dissolve a package or just an amount of sodium hydroxide, NaOH, in water. So first we do that dissolution. That's a decomposition reaction. So sodium hydroxide breaks into sodium ions and hydroxide ions in water. And that's an aqueous solution, meaning that it's a solution, it's not pure water. In this reaction, the system is the reaction of the sodium hydroxide dissolving in water and producing energy. That's the system. This is what we are studying. The surroundings is the mass. It's the solution of the water, the sodium ions, and the hydroxide ions in the surroundings. So that's what's absorbing the heat. It's going into the water mostly, almost entirely, but some of it does go into the sodium ions and into the hydroxide ions. So step 2, this chemical reaction releases heat, Q, into the water. This is an exothermic reaction. So you can see over on the diagram on the right, the heat is going out and it's going to spread out uniformly in the water, right? If you have a bathtub of cold water and you turn on the warm water, the warm is eventually going to spread out and equalize the temperature throughout. Now the sodium hydroxide is shown, just for simplicity, as a single block in the middle of the container there, but it's really broken up into sodium ions and hydroxide ions, that it's a homogeneous solution, so those are spread out throughout the solution evenly. But we do not have a way to directly measure heat Q. So step 3, the heat Q released by the chemical reaction of the NaOH system all goes into the solution, the surroundings. And you can see it warms up over there. This is going to be an exothermic reaction, and it's going to warm up the water. The system, this means that to the system the heat is negative because it's leaving those chemical bonds and it's exiting, so that's exothermic. The surroundings, all the heat leaving the system goes into the surroundings. This means that the negative Q of the system, that is heat going out of the system, is equal in number to the heat going into the surroundings. It's just the sign is opposite. It's positive for the surroundings because the heat is going into the surroundings. Also, no heat escapes the container. So that's what we mean by the universe. It's anything inside that container. It's the system and the surroundings. Nothing outside of that container is a part of the universe as we speak of it here. Step 4, the heat entering the water spreads out uniformly, evenly. This causes an increase in the temperature. So there, over there, you're going to see that thermometer is going to go up. There's an increase in temperature there. So the amount of heat cannot be measured directly. However, the heat can be computed from the temperature change. And there's the formula that you've seen before. So we know the temperature change from the thermometer. We know the specific heat of water. And we're going to use that as an approximation of the specific heat of the solution, which includes the sodium and hydroxide ions. There's not much difference between the two. And then the mass. We need to know the mass of the surroundings, which is the water plus the sodium hydroxide. All of those things are part of the surroundings. And from that, we can compute the Q, the heat, going into the surroundings. And there are the variables. Q is heat, M is the mass of the surroundings, C is the specific heat of water, which we're using as an approximation for the specific heat of the solution, and delta T is the change in temperature, how much the temperature increased or decreased. In this case, it increased. Step 5, this is what we know about the reaction. All heat entering the solution, the surroundings, is equal and opposite to the heat leaving the system. That's the reaction. And all of the energy exiting the system is in the form of heat. And all of that energy came from the breaking of the chemical bonds, breaking and reforming of chemical bonds. So conclusion, the heat computed represents the total energy change of this reaction and comes from the chemical bonds. And a note that in an actual calorimetry experiment, the sodium hydroxide would be spread throughout the solution, not in a single central location, as we mentioned. Okay, so we're going to do a specific example here, and you're going to do one in the lab that's going to be very similar to this. In this case, we're going to use calcium chloride as our solute, and that's an ionically bonded compound. The calcium is the cation, the chloride ions are the anions, and they ionically bond. So we're dissolving 6 grams of calcium chloride in 300 milliliters of water, and that causes the temperature of the solution to increase by 3.43 degrees centigrade. Assuming the specific heat of the solution is 4.18 joules per gram centigrade, and assuming the calorimeter absorbs no significant amount of heat, determine the change in enthalpy for the reaction. Okay, so let's talk about a couple things here. The change in temperature is 3.43, that's the delta T. That could either be in Kelvin or centigrade because the change in temperature is the same on both scales. Now, we need the specific heat of the solution, but there's no way for us to know that. So since the solution is overwhelmingly just water, 99.9% water, we're going to use the specific heat of water of 4.18. And we're going to use that as an approximation of the specific heat of the solution. It also says assuming that the calorimeter, in this case that's just simply a styrofoam coffee cup, assuming the calorimeter absorbs no significant amount of heat. And that is going to be our assumption here. So we don't lose any heat. All right, so let's go ahead and look at this. So step 1, we dissolve the calcium chloride into the water by the decomposition reaction. CaCl2 produces Ca2 plus ions and 2 chloride minus ions. And remember that we do have a conversion that we can use later on in this problem. For water only, 1 milliliter equals 1 gram of water. That's only true for water. Now, what is the system? The system is the reaction of the calcium chloride dissolving in water and breaking and forming chemical bonds. So we're interested in the energy of those chemical bonds breaking and being reformed in whatever fashion that they're doing that. So that's the system. The surroundings is the mass or the matter that's in that container. So that's going to be the mass of the water, the calcium ions, and the chloride ions. Those are all going to be absorbing the heat that's coming out of those bonds breaking and reforming, and that's so that's going to be the surroundings. So step 2, all of the energy given off in the reaction, the system, enters the water, that's the surroundings, as heat. So to the surroundings, the heat is a positive number because it's entering. There is the decomposition reaction. And you'll notice that over on the right in the diagram, it's getting hotter and hotter and hotter. And the temperature goes up. So that heat comes out of the chemical bonds, the energy comes out of the chemical bonds in the form of heat. It spreads out uniformly throughout the water. That is, it's evenly everywhere. And the temperature of the, when I said water, I meant solution. The temperature of the solution goes up. So this is the same amount of heat that is exiting the system, the reaction, into the surroundings. So to the system, it's negative Q, and to the surroundings, it's positive Q. The surroundings is the mass of the water plus the calcium and chloride ions. Step 3. The heat Q released by the chemical reaction of the calcium chloride, the system, all goes into the solution, that's the surroundings. The system, this means that to the system, the heat is negative Q, because it is exiting, so that's an exothermic reaction. To the surroundings, all the heat leaving the system goes into the surroundings, and this means that the negative Q of the system equals the positive Q of the surroundings. The numbers are the same, but to the system it's a negative number because it's exiting. To the surroundings it's a positive number because it's entering. Also, no heat escapes the container. So inside that container is what we mean by the universe. It's the system and the surroundings together. Nothing outside of that container matters to us. No heat is getting in, nothing's getting out. So that's what we call the universe. It's the system and the surroundings together. Step 4. The heat entering the water spreads out uniformly, that means evenly. This causes an increase in the temperature. So we can find the heat from the formula. Q of the surroundings, because we're measuring the heat, the temperature, the heat of the surroundings that's going into the surroundings, equals the mass of the surroundings plus the specific heat plus the change in temperature. And so now we're going to plug in the numbers. So what is the mass? It's not just the mass of the water, which is 300 milliliters of water. That's given to us in the question. And we know we can convert for water only milliliters to grams. So we have 300 grams of water. But it's not just the water, it's also the calcium and chloride ions, and we said we have 6 grams of that. Again, that's up there in the question. So the total mass of the surroundings is 300 plus 6. The specific heat that we're going to use for the surroundings is the specific heat of water, so that's going to be an approximation because there's not much difference, and that's 4.18 joules per gram centigrade. And the temperature change we said is 3.43. Now it's a positive 3.43. That means the temperature is going up. And when you multiply all of that out, you get the Q into the surroundings of 4,387 joules. So we know therefore that the Q coming out of the system is also going to be 4,387 joules. And so down there at the bottom, we say Q surroundings is 4,387, and the Q of the system is negative 4,387. Again, the negative sign just means that the heat is coming out of the chemical bonds. Step 5. Now, we just picked a random amount of calcium chloride, 6 grams. Why do we pick 6 grams? Who knows? We just chose 6 grams. But we want to know the amount of heat of a standard amount of calcium chloride. And a standard amount we've used throughout this class is a mole. So what is the heat if we used 1 mole of calcium chloride? We want to make that calculation. And that's called the molar heat of reaction. And we can calculate that number for the first, we compute the moles of calcium chloride in 6 grams. Now remember, you don't include the mass of the water here. We're only interested in the mass of the calcium chloride. We need to know how many moles of calcium chloride we have. Because where does all the energy come from? It comes from the calcium chloride, the bonds of the calcium chloride. None of it comes from the water. The water is just something that's absorbing the heat. So let's go ahead and do that calculation. So the energy Q of the system is negative 4,387, and that comes from the 6 grams of calcium chloride, not from the water. You got to remember that. The 300 grams of water has nothing to do with this calculation. So the molar mass for calcium chloride, you all know how to figure this out now from your periodic table, is 110.98 grams per mole. So what we can take is the Q of the system, negative 4,387 joules, divided by where all that energy came from, the 6 grams of calcium chloride, and then we can use the molar mass conversion to convert from grams into moles. So when we do that calculation, the grams cancel, and we end up with joules per mole. How many joules of energy do we have per mole of calcium chloride? So that's a standard number that you can look up in a book. And the answer is 81,144 joules per mole. Generally, in thermochemistry, though, we speak in terms of kilojoules, so you divide that number by 1,000, and you get 81.1 kilojoules per mole. And that's the molar heat of reaction for calcium chloride. All right, so that takes care of our lesson on calorimetry. So you're going to practice a few of these problems. Next week or sometime later this week, you're going to go into the lab. You're going to actually perform one of these with sodium hydroxide, and you'll see how this all works.